I was planning to make 4-nitrobenzyl alcohol from 4-nitrobenzaldehyde using a standard sodium borohydride reduction. But then I thought it would be way more interesting to show how deuteration can give direct evidence for reaction mechanisms. So instead of sodium borohydride, I'm using sodium borodeuteride and tracking exactly where the deuterium ends up in the product. By the end, the NMR will literally show us which hydrogen came from the borohydride and which came from the solvent. In methanol, sodium borohydride delivers a hydride to the carbonyl carbon of the aldehyde. The pi bond breaks, forming this intermediate. So overall, the aldehyde carbon gains one H from the borohydride and another H from the solvent or acid workup to give 4-nitrobenzyl alcohol. With sodium borodeuteride, the same sequence happens, but now the hydride is deuteride. So we expect the product to have 1D from the sodium borodeuteride at the benzylic carbon and 1H from the methanol or acid workup at the same carbon, giving a CH-DOH group. Hydrogen has two stable isotopes relevant here. Protium, the usual hydrogen, 1 proton, no neutrons. Deuterium, heavy hydrogen, 1 proton, 1 neutron. Chemically, they behave almost the same, but deuterium is about twice as heavy, which slightly changes bond vibrations and reaction rates. To start, I added 1 gram of 4-nitrobenzaldehyde, then added just enough methanol to make a slurry, about 8 ml. After that, I dropped a stir bar and started stirring. To begin the reduction, I added 300 milligrams of sodium borodeuteride. Now two things are happening in parallel. Deuteride attacks the aldehyde carbon, forming this deuterated intermediate that will become the product. Deuteride also reacts with methanol, generating methoxyborate species like sodium tetramethoxyborate and HD gas. Because some deuteride is wasted on the solvent, I used an excess of sodium borodeuteride to push as much of the aldehyde to the product as possible. Not all the sodium borodeuteride ends up reducing the aldehyde. Some is consumed by the solvent, so excess helps maximize conversion. A few pointers to make is adding a bit of sodium methoxide to the methanol can suppress borohydride decomposition by preforming methoxide. In the reaction, I also use cold methanol to further limit decomposition in methanol. After about an hour, most of the gas evolution had stopped. To liberate the product from the borate salts, I added 8 ml of 18% hydrochloric acid. The acid protonates the intermediate and decomposes borate complexes, freeing the alcohol. I dropped in a chunk of dry ice to cool the solution during acidification, but that's totally optional. Cold water or an ice bath would work fine. I then added 20 ml of water, which helped crush out the product as a precipitate. I collected the solid by vacuum filtration, washed and dried it, isolating 700 milligrams of product. In the proton NMR, the aromatic region shows the expected para-disubstituted pattern. The key change is at the benzylic position. In normal 4-nitrobenzyl alcohol, the CH2 group appears as a 2H signal around 4.6 ppm. In my product from sodium borodeuteride, that benzylic signal integrates to 1H. That tells us one position is for deuterium for the sodium borodeuteride, and the other is a proton from the solvent or acid workup. In the carbon with proton decoupling spectrum, the benzylic carbon shows a signal around 60 to 65 ppm with subtle splitting and broadening compared to a normal CH2 carbon, again consistent with a carbon attached to a deuterium. This was a really satisfying reaction. Using deuterium this way is a powerful tool to prove or disprove a proposed mechanism. Thanks for watching.